Welcome. I'm Megan Inslee, Senior Technical Project Manager with Thermo Scientific. I'm excited to be your moderator today. We've got a great session lined up for you focused on how probabilistic genotyping can bring clarity and confidence to DNA mixture interpretation. Joining us are two incredible experts in this space. First, we'll hear from Dr. Mike Coble, the Executive Director of the Center for Human Identification at the University of North Texas Health, Fort Worth. With nearly 3 decades of forensic DNA experience, Mike has contributed to some of the field's most significant cases and advancements, including 2 historical cases, the missing Romanov children, Maria and Alexei, and the unknown child of the RSS Titanic. We're also joined by Dr. Chantel Roth, Senior Bioinformatics Software Engineer with Thermo Scientific. Chantel's background in scientific computing and forensic genomics has been key in developing the algorithms behind GeneMapper and next-generation sequencing analysis software. Her career spans a wide range of fields, from robotics and genomics to physics simulations, and a passion for using advanced computational tools like AI to solve real-world problems. Together, they'll walk us through the challenges of mixture interpretation and how deterministic PG can make results more transparent, reproducible, and defensible. With that, let's kick things off. I'll hand it over to Mike to get us started.
Thank you, Megan, for the very kind introduction. So I'm going to go through sort of an introduction of probabilistic genotyping. Historically in forensics, we have made huge investments in technology. We have big kits now that test 20 plus loci. We have capillary instruments that can be very sensitive. We have new dyes and new technologies. But historically, we've made very few investments in interpretation. And so using this sort of sumo wrestler theme, it's an unfair fight, really. We haven't really taken a lot of time to catch up with our interpretation of especially DNA mixtures. One of the critical statistics that we examine when we're doing probabilistic genotyping is the likelihood ratio. And it's simply an evaluation of the probability of the evidence given one hypothesis divided by the probability of that same evidence given an alternative hypothesis, H2. And so we look at this ratio, and when we're doing our interpretation, say, for example, our evidence is 1213 and our person of interest is also 1213, we can easily see the probability here in the top part of our likelihood ratio is 1. And for the alternative hypothesis here, we will look at, instead of this individual, we'll look at a random man in the population. So our likelihood ratio in this particular single source easy sample, well above our stochastic threshold. Our likelihood ratio is 1 over the RMP. Now, if we have discordance between the evidence and our person of interest, well, for our top part of our likelihood ratio, it's impossible for someone who's a 1215 to give evidence that is a 1213. So in this case, our likelihood ratio becomes 0. And we call this the binary approach because notice you're either 1, that is inclusionary, or 0, exclusionary. And so kind of like computer code, it's 1 or 0. The question, though, comes, what happens when you have data that's below your stochastic threshold, where there is now a possibility of alleles dropping out of the profile? So we see the 12, it's below my stochastic, there may be dropout. And when we align this with our person of interest, there's now uncertainty. I mean, traditionally we would say something like, oh, well, yeah, it's him, it's just there's dropout. And so we would assign a 1, probability 1 to the top part of our numerator here in our likelihood ratio. And for the denominator, we would say, well, we can use the 2p rule. And so our likelihood ratio becomes 1 over 2p. But many people have questioned whether this is really the best way forward. Because again, that 1 means certainty when we're talking about probabilities. And since we have uncertainty, maybe this value shouldn't be 1. Maybe it should be 0.5. We're halfway there. We've got the 12. We're missing the 13. And we also know that in some instances, using the 2p rule is not always conservative. So we're at a quandary. How do we interpret data when there's the potential for missing information? Should we continue to use historical methods like CPI, random man not excluded? Probably not optimal. Not to say that these were wrong, it's just that we end up throwing away a lot of information. What about using the likelihood ratio with the 2p rule? Well, as I just mentioned, sometimes that 2p rule is not always optimal. So if we're going to throw in a little meme here, we could probably do better. Well, maybe we should be looking at probabilistic methods of interpretation. That sounds much better to me. What is probabilistic genotyping? Well, according to Swigdam, it's using biological modeling, statistical theory, computer algorithms, probability distributions to calculate that keyword likelihood ratios and try to infer the genotypes from the typing results from your evidence. Keyword, it's a tool. It's something to help the analyst. It's not meant to rule the analyst. It's a tool that we can use for interpretation, and therefore we can help in our investments in interpretation now. We also provide statistical weighting to different combinations, but the key word here is we no longer need to use a stochastic threshold. We're going to interpret these peaks probabilistically. I like to quote here Dr. Dennis Lindley, who was really the father in Bayesian analysis in the modern times. And this quote from his book, Understanding Uncertainty. Whatever way uncertainty is approached, probability is the only sound way to think about it. And as I mentioned, when you have uncertainty in your profile, we need to be thinking about this now in terms of probability, hence probabilistic genotyping. There are different ways that we can interpret profiles probabilistically. We're going to focus today on continuous models. That's where we're modeling the sort of molecular biology of the profile to try to find the optimal genotypes. Now, there are two ways we can do this. We're going to talk about weighting certain genotypes, or we're going to talk about finding the maximum likelihood. There are multiple software programs that are out there now. When I started talking about probabilistic genotyping well over 10 years ago, there were only 2 or 3 models or 2 or 3 software programs. Now, there's approaching well over a dozen. And this is not exhaustive. There are probably some that I don't have on this list. But we're going to focus on 2 approaches. The ones here in green use what's called the Markov chain Monte Carlo approach. The other software programs use this maximum likelihood estimation. So the Markov chain Monte Carlo is using a set of parameters, things like this set of genotypes, degradation, how much template, and try to produce estimated peak heights that you expect to see given these parameter values. And then from that, we'll determine which of these parameter values best explain what we observe. The maximum likelihood estimation approach tries different combinations of contributors and again uses other parameters to calculate likelihoods for each scenario and then lands upon one scenario, one likelihood that is the maximum. So we're going to give just a very brief overview of each of these. First, the Markov chain Monte Carlo methods. These methods will randomly vary a set of genotypes using these parameter values to produce expected peak heights. We then compare what we expect given these parameter values in the genotype set to the actual peak heights we observe, the peak heights in the evidence. So we're generating some expected peak heights, and then we compare to the observed. And then we'll use an algorithm. It's called the Metropolis-Hastings algorithm. So the first part of this, the Markov chain Monte Carlo, is we're generating randomly peak heights based upon a set of parameters. And then we ask the question, is what we expect very close to what we observe, or is it way off? And from there, we'll either accept these parameter values or we'll reject them. And so it's that process of accepting or rejecting is where this algorithm comes into play. Here is some output from a mixture using a probabilistic genotyping software called StarMix. And at this particular locus, it's a two-person mixture. I know this because this is a mixture that I actually created in the lab, so it's not a real casework sample. So I know the ground truth of the individuals in this mixture. Notice there's a very large peak, very large allele here at 12, and then there is an allele at 11, which is in the stutter position for the 12. So when the software is trying to determine the two individuals that make up this mixture, it lands upon 5 different combinations. And the first combination we'll look at is the major contributor here, in this case, our complainant, is a 12-12. And the minor contributor coming from my person of interest, the software has determined this first genotype to be 11-11, which means that 11 allele is considered to be allelic and not a stutter artifact. And the software, the way I like to think about this is it landed upon this particular combination about 4% of the time when it was doing all of these simulations. Again, I'm doing a little hand waving here because we don't have enough time to go through all the details. But if you notice from this list of 5 combinations, there's one in particular. The complainant is a 12-12, and the unidentified person of interest is an 11-12. That is, that 11 is allelic, plus maybe a little bit of stutter, but there's also a 12 allele that is shared along with the complainant. About 74% of the time or so, the software sort of landed on this explanation. Again, doing all of the things that it's doing. Now, the truth is, when you now compare my person of interest, who happens to be an 11-12, that will now be used, this weight will be used in determining or assigning my likelihood ratio. So for my likelihood ratio here, I'm going to take the weight of this particular combination of 2 people, a 12-12 complainant and an 11-12 person of interest, and that now 0.7428, that weight is now my numerator. So we say the complainant has a probability of 1. I did condition, or I did assume that she is part of this mixture. And for the unknown individual here, my person of interest, who aligns with the 11-12 genotype, we're going to use this 0.7428 as the weight for my numerator. For the denominator, we're simply going to take all of the genotypes for this unknown contributor now, an 11-11, an 11Q. I should explain that Q represents an allele that is not observed. So it could be a 13 allele, it could be a 9 allele, any allele that you don't observe in the evidence. So we're going to weight each of these genotype combinations by this value. So we're going to multiply 0.0441 times the Hardy-Weinberg p-square for an 1111. And then we'll multiply the weight of 0.0007 times the Hardy-Weinberg for a Q11 genotype, and so forth and so on. And that's how we build our likelihood ratio using these weights that we have determined from these simulations, these random simulations of the data using that Markov chain Monte Carlo. We look at a very low level contributor in a mixture with a very high female background, and we see that if we're using the old approaches, what I mean by that, if we're using a stochastic threshold, we're going to throw away about 80% of this data. And so we're not really making the best use of the information present in the profile. When we use a probabilistic genotyping, in this example, star mix, but again, there are other examples that you can use, we get a likelihood ratio here of 1.5 million. The other approach I mentioned is the maximum likelihood estimation. The easiest way to sort of explain this, I'm going to bring it back just a little bit and not talk about DNA for a moment. Suppose I have a container, and in this container I have some colored marbles. I have 4 red marbles and 3 blue. Now, I let you look inside of this container, and you can count and you can see that there are 4 red and 3 blue of the 7 marbles total. So I wanted to ask you now a question. Here we go. This is our evidence. I want to ask you a question. What's the probability of reaching into that container? Close your eyes, reach in the container, and pick out a red marble, then reach in and pick out a blue, and then reach in and pick out another red. So that's my hypothesis. What's that probability of picking a red, blue, red combination, given the marbles that you have here in my container of both red and blue? Well, we can actually calculate this. We can calculate the probability that the first marble you pull out is a red. Well, there's a 4 out of 7 probability that that's a red marble that you pull out. We now subtract 1 from the total marbles. We pulled out 1. Now there's 6 left. What's the probability of pulling out a blue? Well, now the blue, there are 3 blue, 3 red. So it's now 50-50, 3 out of 6. And then finally, we've pulled out a marble. So now there are 5 left. We pull out the last red one. And there are now 3 red marbles left and 2 blue. So it's 3 out of 5. So the probability of me reaching into this container and pulling out 3 marbles in a row, no replacement, red, blue, red, is about a 17% probability here, or likelihood. So there's a 17% chance you would win the prize of picking out a red, blue, red the first time you try this. Now, that's pretty simple because we know what's in the little container. What if we don't know? What if all we know is that there are 10 marbles in my little container, and I'm going to make it a little bit more complicated. We have, I'll tell you, okay, there's red, there's blue, and I'm throwing in a little purple marble as well. So you don't know how many of each type is in this container because I've hidden that from you. So what's the probability now? Because our evidence is unknown, we don't know what the colors are. What's the probability of the evidence given a hypothesis? Again, my hypothesis is I'm going to pick out here blue, red, blue. Okay? How many red, blue, and purple are in the box? I don't know. I don't know. You won't let me see. So we're going to use likelihoods to determine this possibility of picking out a blue, red, blue. Now, some facts here. There's 66 combinations if you have 10 little marbles of 3 different colors. So that includes all the possible permutations and combinations of picking out 3 marbles. But we're really only focused on the ones that are blue, red, blue. And so the first time we pick out a marble, there are 10 marbles there. The second time, there's going to be 9 marbles. And then the third time we pick, there's going to be 8 marbles left. But notice not all of these 66 combinations are possible or valid. For example, if all 10 of those marbles are purple, you will never pick out a blue, red, blue. So some of these possibilities are invalid. They will never happen because of the combination of colors. So let's focus only on the combinations where we could pick out blue, red, blue. So we can go through for the first example here. Suppose there's 1 red marble, 2 blue marbles, and then there's 7 purple. So you've got to be pretty lucky now to reach into that box and pick out 1 blue marble out of the 10 total. And then you reach in again. Now there are 9 marbles. You pick out the 1 red, the only red marble that's in there. And then lastly, now there are 8 marbles left, 7 purple and 1 blue. And now I have to be lucky and pick out that 1 last blue marble. So you can see the probability of reaching into a box with 1 red, 2 blue, and 7 purples is pretty low. 0.0027. So it's very, very low likelihood that you would find that combination given the colors of 1 red, 2 blue, and 7 purple. Well, we can go through and calculate the likelihoods for each of these combinations. And notice there's 1 here. When I have 3 red marbles, 7 blue, and 0 purple, my probability of getting the right combination of blue, red, blue is 17.5% of the time I could do that. I could pick out 1 blue, 1 red, and 1 blue. Again, no replacement. This is the highest likelihood here for my combination if I have this optimal color scheme. And so we call this the maximum likelihood. That is the scenario where I have the best probability of picking out that blue, red, blue. Okay, you're asking, how does this apply to mixtures? And what are software that, what do these software programs that use this approach, how are they doing it? Well, let's do a little quick example. Suppose I have a mixture of 2 people, and I have 2 alleles that are present, A and B. And I have a person of interest who is an AB, and my unknown contributor, I don't know who it is. We're not saying it's a complainant or a victim here. We're just saying there's another person in this mixture. I don't know who it is. My person of interest is AB. So what the softwares will do is using the model parameters, which is this in this sort of table here, that's the first column that says theta. So it's using the model parameters if the contributor was a 20% contributor, 1 in 5, or a 40% contributor, or a 50% contributor. So it's looking at different combinations of 2 contributors, the ratio of, in this case, major minor, or maybe at 0.5, you're 50-50. And what it does is it calculates a likelihood given these model parameters. And you can see on the far right of this table, we're taking the log likelihood because these are really small numbers. So we want to make them a little bit bigger. So we can take the log and notice the one that is the maximum is the 50-50 here, where you get a maximum likelihood of minus 16. That's the highest. Now it's at, well, wait a minute, you're negative, but negative 16 is a bigger number than negative 19. So we're looking at the optimal ratio here in this mixture. It would be someone who is a 50-50 mixture in this case. Again, we're using the other parameters as well. Next, that was for H1, that is if my POI is in the mixture. What if it's 2 random people in the mixture? So we'll do the same thing. We'll maximize the likelihood for H2. And from there, we'll get our likelihood ratios. So just to sort of look at what's happening, you're looking at ratios over a range from a 10% contributor to a 90% contributor. And the software is trying to find where as the maximum, what's the best explanation over this range of contributors. And in this case, it's at a ratio of 0.7 to 0.3 in this case, 70% major contributor. So to wrap this up, probabilistic methods of interpretation make better use of the data, that is from the evidence, than previous threshold-based methods of interpretation. We're not trying to get big numbers here. That's not the goal. The goal of using a probabilistic method of interpretation is to make better use of the data, not simply drawing a line across the profile and throwing out loci because the peaks don't meet or exceed this threshold. So we no longer need that threshold. We're using all of the data, which is a good thing. Now, this approach is rapidly being adopted. I can speak about the US. It's become now the new standard for interpretation. There's about 75 to 80% of forensic DNA labs in the US are using, have either in the middle of validating or have validated and have implemented probabilistic genotyping software. It's also being used globally. So it's becoming, if it hasn't already, now the new standard for interpretation. So we've now stepped forward. Our sumo wrestlers are a little bit more evenly matched for the kind of samples that we're able to generate data for. Of course, it's necessary and important that you understand likelihood ratios and be able to properly communicate that to the trier of fact for our stakeholders, not just in court, but also for the medical legal community as well, so that they understand what this means. Thank you so much to Thermo Fisher, and also thanks to my colleague Joe Bright and my colleague at CHI, Brianna, and I appreciate the time. I'm now going to turn it over to Dr. Roth. Thank you.
Thank you very much, Dr. Coble, for the background introduction. As Dr. Coble mentioned, my name is Chantal Roth. I'm a senior bioinformatics software engineer from Thermo Fisher Scientific, and I would like to give you an insight into GeneMapper PG and how it interprets DNA mixtures, in particular deconvolutions, likelihood ratios, and number of contributors. As Dr. Coble has shown, there are different modes of how mixtures can be analyzed. The simple binary mode, where only the absence or presence of alleles are used, is often insufficient for complex mixtures. GeneMapper PG uses a fully continuous model where all information of the profile is used, including peak heights and where drop-ins and dropouts are considered as well. Dr. Coble has introduced two approaches, MCMC and maximum likelihood estimations. GeneMapper PG is based on a maximum likelihood approach. Conceptually, it is very similar to a manual interpretation. It is a forward, physically based maximum likelihood method, and it compares expected and observed peak heights. Now, the easiest way to explain this is really with an example. Note that all the images I'm going to show are actually screenshots from the software. And also what I'm going to show is very close to what GeneMapper PG is actually doing. So let's imagine we have a mixture of two. And let's imagine further, the mixture ratio was about 4:1. And of course, we'll go into the details later, how we determine the number of contributors and the mixture ratio. So I think you will agree with me mostly if I say, in this case, it's pretty clear. The major is probably going to be 2324. And a pretty good minor is probably going to be 19 and 27, because the 22 can be explained by stutter. So the software will go through all the possible genotype combinations that make sense in this particular context. In this example, it picked 23 and 24 as major, and it picked 19 and 27 as minor. Now note these little orange peaks. It actually adds the stutter peaks as well. What it then does is it combines the major plus the minor together, gives a expected profile, a computed profile. Note that it also has all the stutter peaks. What the software then does, it compares this expected profile with the actual evidence profile. But how can it do that? I mean, how does it know where to put stutter and how much? This is where the statistical model comes in. It is really the core piece of the software. It describes how peaks behave, what stutters to expect per locus and per allele, how much noise is expected, and so on. It also describes degradation, pull-ups, shoulder, and the noise model is dependent on the amount of DNA, and so is the peak height model. Here's an example from the software. As a user, you can actually open the statistical model and you can take a look at all the values and all the stutters and the dropout behavior, drop-in behavior, and so on. Here is an example of D3, the back stutter. You can see the mean and the standard deviation. Here's another example of SC33, and you can see it's a little bit more complex. We support forward stutter, backward stutter, double back stutter, and half forward and back stutter. We also have a model for the peak height ratios. Now, the interesting part here that it depends actually on the amount of DNA. Because as you see on the left side, when you have low amounts of DNA, the distribution is really wide. That means the peak heights can be very widely. On the other hand, when you have a large amount of DNA, the variance is much smaller. So the software will determine how much DNA is approximately in the mixture and use the appropriate models. So now that we have an idea of the statistics, so what does the software do? So for a particular number of contributors, such as 2, and the ratio, such as 1 to 4, the software will then enumerate all the plausible genotypes for these contributors and for this particular context. For each candidate genotype, it will compute the expected profile. The result is then compared to the observed profile. And then it computes a likelihood of the observed profile under the statistical model for that genotype configuration. And the result is a list of all possible genotypes sorted by likelihood. And the overall likelihood score for a candidate profile is obtained by multiplying the locus-specific likelihoods across all loci. To get a better understanding of this, let's make another example that's a little bit more complicated. And I want to use this to explain to you the different kinds of score we're using. Now, you can probably see right away that the major is pretty clear, but the minor, there seem to be multiple possibilities. So again, the software will look at this. It will go through all different combinations. And you can see that these first 3, they look all pretty reasonable. They have a good fit. They have a high likelihood. But all of them are not perfect. You can see here the 9 is not tall enough when you compare to the evidence profile. Here, if you pick 9,9 as the minor, it is to be too tall. So they're all not perfect, but they're pretty good solutions. The software will continue then to go even to crazier solutions. It will, for instance, also consider 1013 as minor. It will consider 1010 as minor, and so on, until it gets so bad that at some point it's going to stop. It will stop when the solutions are impossible. For instance, imagine you had a peak of height 3000 and your solution had to explain a drop-in of that size. Then, depending on your settings, that is totally controllable by the user, it will then stop the iteration of the genotypes. Here is a screenshot of the software for this particular locus we just talked about. And on the right side, you can see one of the solutions. You can, of course, look at all the solutions. So what do all these numbers mean here? On the left side, you can see the likelihood scores that we just talked about. The results are sorted in decreasing order, so we can see the best solutions on top. Now, if you want to extract the major profile, for instance, maybe you want to do a database search, or maybe you actually want to add this major profile as a profile to your list, you can then use this top solution and export it. Now, in some cases, though, it might make sense to look at multiple combinations. For instance, the major is pretty clear, as you can see. There's always a 10 and a 13 in almost all the solutions. And this, when we add up those numbers and normalize it, that's when we get the weight. So you can see, for instance, the major is very clear. It's probably going to be a 10 and 13. Now, for the minor, however, as you have seen before, there are multiple possibilities. It's probably going to be a 9. You're pretty sure about that one. But the second one, well, it could be a 10 or it could be a 13. And in fact, the true solution is indicated here in yellow. It's actually a 13. But of course, you wouldn't know that unless you had the truth. And in some cases, it can then be useful to say, you know what, I'm going to export either, depending on your lab settings, I just want to use the 9, or I'm going to include 9, 10, and 13. So we have just talked about two types of scores. We have talked about fit, which is the likelihood I've just talked about. This is the absolute score. Everything is sorted by this absolute score. It ranks complete genotype solutions, and the question is really that we ask is, well, how well does this particular solution explain the evidence? The weight, however, is a normalized score per allele. It's across multiple solutions. And this really measures the robustness of an allele assignment. The question we can ask here is, how confident are we in this allele for this contributor? Each one of them has advantages. There are cases where it's really critical that we use them. For instance, imagine we pick the wrong number of contributors. Even the weight might be great. Maybe there's only one solution. Maybe you can only pick a 10, but it's really awful fit. So in that case, the likelihood would be very low and the weight could still be high. So it's good to use the likelihood as a measure of how good the assumptions were that we made for this particular scenario. We might also make a mistake and use the wrong conditioning, use the wrong profile. And again, the weight might be 100%, but the fit again would be really awful. On the other hand, it can happen that there are many, many good solutions. The likelihood is really great. But there's so many possibilities, which can happen when you have, for instance, a 1-to-1-to-1-to-1 mixture. And in this case, the weights would all be small. So both scores are really important. So far, we have used a particular ratio in the example, but how does the software know what ratio to use? Dr. Coble has talked about MCMC. And this is a common approach used where there is a sampling process that tries to find the optimum. The thing is, there is some variability, and you will have to use diagnostics to make sure that your chains converge. We have decided that for us, reproducibility is really important, transparency is really important, and we wanted to have a deterministic approach. That's why we have decided to use a grid-based approach. This is how it works. Here's an example of a 3-person mixture. The x-axis shows the ratio of one contributor. The y-axis shows the ratio of a second contributor. And the surface you see here, these are the likelihood scores. And the goal is to find the maximum. We want to find the maximum likelihood. And the approach we are using is we use a grid-based approach that deterministically finds the optimum. The good thing about this, it's very easy to explain. It's stable. You always get the same result. Now, there are other software that also use a maximum likelihood approach. So what's the difference then? In our case, we use a prediction. We predict what the electropherogram should look like given mixture ratios. It then compares it to the data. Other software, sometimes they would infer the parameter values that make the observed peaks most likely under its stochastic model. Another difference is the genotype handling. We enumerate the genotypes based on the context, so based on the current situation of the ratios, for instance. That means we don't have to look at all the combinations every single time. Other software sometimes would enumerate all genotypes up front. Now, in terms of computation, because we can use context pruning, it tends to be pretty fast. Of course, there are exceptions. If it's a 1-to-1-to-1-to-1 mixture, there's no advantage. We really like the idea that it's physically intuitive and transparent, so you can look at all the solutions, and that's why we have chosen this approach. So far, we have only talked about deconvolution. So what about likelihood ratios? For likelihood ratios, deconvolution is also used as one part of it, but the focus is a bit different. Whereas for deconvolution, the goal is, for instance, to extract the most likely contributor, to analyze the mixture and to do database searching. For likelihood ratios, we are comparing two different hypotheses. The goal here is a bit different. It's really to get a numerical likelihood ratio value, to get the weight of evidence. Dr. Coble has already covered likelihood ratios, so I will not go into more detail here. We follow the framework described in forensic DNA profiling by Dr. Coble and Bright. Now, while some systems use the Dirichlet priors to model uncertainty in allele frequencies, they treat population frequencies as a random variable and integrate over them during sampling. GMapper-PG follows the Baldwin-Nichols formulation, which provides a similar population correction analytically and deterministically without random sampling. Here is an example screenshot from the software. On the left side, you can see you can define your prosecution hypothesis. On the right side, you can define your defense scenario. And you get the typical result with a table where you see the likelihood values per locus, and you can see the overall log likelihood ratio. Because we value transparency, there's an option in the software that lets you introspect all the calculations. Here's an example. You can see that it was looking at the combination 17 and Q, where 17 is the dropout allele. You can see the formula from the Baldwin-Nichols with the actual frequencies used. You can also see the fit score, this is the likelihood, and the resulting product, and the ratios used. There's also an option to have even more detail. You can even check all the steps the software is doing, all the calculations. How is it calculating the dropout probability? How is it calculating the drop-in probability, and so on. Now, so far, we have only looked at an illustration of the surface of the likelihood score based on the mixture ratios. Now, GeneMapper PG also actually generates that for 2 and 3 person mixtures. So this is a real surface, what the real surface looks like. Here we have the likelihood for the defense, we have the likelihood scores for the prosecution, and this is the overall, the log likelihood ratio. And you can see, for instance, let's say your ratio was, 0.8. You can see whether it matters whether you use 0.8 or 0.7. And in this case, you can clearly see it doesn't really matter that much. Whether your solution is 0.7 or 0.8, the solution is really stable. That's important to know. Now, even if the LR supports the prosecution, sometimes the defense might still ask, well, what if the brother did it? What if there was an unknown child or sibling? So what we do, we have something called robustness analysis. What it does, it lets you visualize all the log LR values for all the possible contributors. And you can compare it to the score that we have for our person of interest. It will also let you simulate siblings. You can, for instance, simulate 10,000 siblings or 10,000 children, and then look at the distribution of the result and compare it to your current result to get more confidence if the result makes sense, or if there is, defense has a point that maybe it was a brother. So how does the overall workflow actually look like? We have integrated GeneMapper PG into the workflow so that you do not need to worry about exporting and importing. So that means you would still do your primary analysis in GeneMapper IDX as before, and then you can push the samples through a plugin to GeneMapper PG automatically. Of course, you can still import other file formats if you like. Now, in a normal workflow, before you can run any deconvolution or likelihood ratio analysis, you need to determine the number of contributors. And so far, we have simply assumed a certain number, like 2. So how does that work? When you look at this profile, what do you think how many contributors there are, and how would you approach it? As you probably know, there are many different challenges to number of contributors. Of course, in the ideal scenario, we had exactly, each peak was separate. We would see all the peaks. There would be no dropout, no noise, no drop-in, and then it would be easy. You could just count the peaks and you get the number of contributors as 2 here. But a lot of things can go wrong, especially when you have low amounts of DNA, or if the mixture ratio is really extreme, then your minor might drop out. It might fall below the analytical threshold. And then it might look like number of contributors -1. There could also be allele sharing. For instance, especially when you have a family, parent and child, then of course, then some alleles are going to be hidden. And again, it will look like a NOC -1. And unfortunately, we also get sometimes extra peaks, in particular noise peaks and stutter peaks, which makes it look like number +1. So how is this handled in GeneMapper PG? Now, there's no single algorithm that can determine the number of contributors in every situation. Instead, GeneMapper PG provides multiple complementary algorithms, each examining the data from a different perspective. Some are rule-based and traditional, others use machine learning. Together, they provide the expert with a well-informed, transparent basis for determining the most plausible number of contributors. Let's take a look at some examples. The easiest algorithm is the maximum allele count, which you're probably all familiar with. The one difference is that we first filter the profile. Now, this is just filtering for the number of contributors. It's not filtered for deconvolution or likelihood ratios. That one is very easy and often used manually in the laboratory. Another standard algorithm is the total peaks. The idea is that as your mixture gets more complex and your number of contributors increases, you also get a larger number of total peaks. What the software does, and I will talk a little bit more in a minute about this, it will simulate thousands of mixtures that look similar than your evidence profile. It will plot the total number of peaks for each, so for one contributor, for two, for three, four, and so on. It will then compare it to where your evidence profile is, and that can help you determine whether it looks like a single contributor or a mixture. We also added 2 machine learning algorithms, which we chose 2 levels, 2 types of decision trees. Because even though they use machine learning, they are transparent and understandable. Decision trees are kind of like flowcharts. You can understand the logic. Again, the profile is first filtered, and then we use simulation to train the decision tree on the fly. At the end, after running all the algorithms, GeneMapper PG displays a summary view showing how each algorithm reached its conclusion. In some cases, the result is straightforward. All algorithms agree on the same number of contributors as shown on the left side here. In other cases, the outcome may be less clear, like on the right side. Here, you may want to inspect the data more closely or analyze the mixture and alternative assumptions to confirm the result. Now, how do we actually train these machine learning models? Is there enough data? There's a big risk in machine learning because if you don't have enough data, if you don't cover all the situations, you will end up with bias. And if you do the calculation of how many samples would you need to make sure you cover all the populations, all the proportions, all the amounts of DNA, all the kinds of degradation, and so on, you end up with an astronomical big number, like 70 million or even more. Of course, that's not possible. No lab can produce that kind of data. And the thing is, if you don't use enough data, you end up with bias. You will then train your model to your laboratory, to your validation set. But when a case, for example, comes in that's different, it will not work well. Now, we actually know quite a lot about the profile even before determining the number of contributors. For instance, we can estimate the amount of DNA, the DNA quantity, from the total peaks. And we can also assess the overall degradation of the sample. Plus, we have a very detailed statistical model, so we can actually simulate very realistic profiles with similar characteristics to support and train the number of contributor algorithms. So the way it works is the software will look at the evidence profile and generate thousands of similar profiles using the statistical model, and then use that, because when it simulates, it knows the truth. It will then train the decision trees using that simulated data. So in summary, we start with a continuous probabilistic model that describes the entire profile, including stutter, noise, and population statistics. The mixture search, which I wasn't able to show you due to time constraints, it lets us quickly compare many evidence and reference profiles for triaging and also for staff elimination. For the number of contributors, we use multiple complementary algorithms, both traditional and machine learning, to support the expert judgment. The deconvolution step identifies unknown contributors in a mixture and can also produce deconvoluted profiles suitable for database searching. And finally, likelihood ratios quantify the strength of the evidence using the same deterministic framework, including robustness checks with simulated relatives. Altogether, the system is transparent, reproducible, and designed to support clear forensic interpretations. Thank you very much for watching, and we may have a bit of time to answer a few questions.